Okay, again, so we're trying here to look at the bondization energy when the carbon hydrogen is being broken by a homolytic bond cleavage. And here we are trying to compare what is the bondization energy of a propene to produce an allylic radical as compared to other alkyl radical. So here the propene again will have a bondization energy to produce an allylic radical, can use H bond, having a homolytic bond cleavage, you have the 369. No, if you try to compare it to isobutane, no, where you have 3 carbons, also you have 3 carbons, and you produce a 3-degree radical. You notice the value of the bond dissociation energy is much lower than 400. Okay, and we've already established before that a 3-degree radical is much more stable than a 2-degree radical and a 1-degree radical. Okay, so if you try to compare isobutane, propane, and propane, propane, of course, and propane, no, to produce 3-degree radical, isobutane to produce 3-degree radical, canning bonds H1, and propane to produce the 2-degree radical, isopropyl radical here, and propyl radical here. You notice that the bond dissociation energy to produce a 3-degree radical is much lower. You see, 400 kilojoules per mole, and this one for a 2-degree radical is 413, and this one, 1-degree radical is 423. Okay, so we have already established that there is much stabilization forming a 3-degree radical. See, the 400 is much lower than 413 or 423. And you noticed here that for all this, the allylic radical actually that's being formed, or allyl radical or allylic radical, is much lower. So we can say that there is much stabilization in the formation of allyl radical. Okay, because here you have a much lower bond dissociation energy, and the highest one is actually the vinyl radical. You have your CH2 dot, CH dot rather. You have a very high bond dissociation energy. So this one is very not unstable, but we see that for allylic radical, it's very, very stable. So what could be the reason for this? Of course, you have a pi bond here, where there is a sideways overlap of the unhybridized p orbital between these 2 carbon, sp2 sp2 carbon. For this carbon, no, and of course it utilizes an sp2 carbon, that there is an unhybridized p orbital with this one. Okay, so they will do sideways overlap, and imagine if there is a unhybridized p orbital of this here carbon here, containing 1 electron. So it will do electron delocalization with this adjacent also unhybridized p orbital in such a way that you can actually yield canonical structures or contributing structures or hybrid structures, or resonance structures. In particular, with this allylic radical, you can have your C double bond, CH double bond, CH2 here, and you have the radical here by pi electron delocalization. So look at in the next slide. I think there is an illustration. Okay, so how is the, okay, so we'll look at in the next slide now, how is the stabilization by pi electron delocalization happens with an allylic radical. But for now, we'll look at the bondization energy with forming the allyl radical and the vinylic radical. You can see here that the formation of vinylic radical, the bond dissociation energy to form the vinylic radical is very high as compared to the allylic radical. So it's much more stable. The allylic radical, again, is much more stable than the vinylic radical. And here is the relative stability of an alkyl radical compared to 1 degree, 2 degree, and the vinylic radical here. We have already seen that one. The bondization energy for allylic radical is 369 kilojoules per mole, so which is much lower. And this is also equivalent to its potential energy here. Okay, so it's much more stable. then the 3 degree, again the 2 degree, 1 degree, and the vinylic radical. And we can say that with the ace of the allylic carbon hydrogen breaking of the CH bond by homolytic bond cleavage, no, the most stable is the allylic or the allyl radical here. So the allylic radical is much stable than the 3 degree, then a 2 degree, then a 1 degree, or a vinylic radical. The reason that allylic radicals are more stable than alkyl radicals is due to electron delocalization. And we can draw actually contributing resonance structures. No? So you have here the carbon containing the dot can actually have the delocalization, can have share the 1 electron from this pi bond here to have your double bond, and you have your radical on this side. And these are the 2 contributing structures that if we take into consideration into these 2 contributing structures, we actually get the resonance hybrid of these 2 structures like this one. So the electrons that is initially contained, as we have seen earlier on this kanilang carbon, it's actually, this radical is only contained in this carbon because of the resonance structures or pi electron delocalization. It's actually what we call as delocalized throughout these 3 carbons, that such a way we can have a resonance hybrid for these 2 contributing structures. And because of that, the charge or the electrons is being dispersed by what we call as pi electron delocalizations. And you can say that resonance delocalization of allylic radicals means that bonding of the hydrogen can occur at either end of the allylic radical. So because you see your radicals, your dot can be formed in either this kaning end or kaning end. Well, it doesn't form kaning sa tunga. So because of that, you can have your halogen, bonding of the halogen can occur at either of this end. So with allylic radical from propene, there are 2 possible substitutions. There are 2 possible substitutions, but of course the 2 are just the same. But whenever you have an unsymmetrical allylic radical, no, pag unsymmetrical siya, like this case, either diri siya mo form or diri siya mo form of another halogen, the same ratong product. Pero kung naatay unsymmetrical, no, nga allylic radical, we actually have constitutional isomers being formed. For example, here, no, you can have your CHC double bond carbon here, and you have an allylic position here. Here you have your carbon double bond, another carbon here, and here is the allylic position. Here you have 2 allylic positions. You have here and you have here. So imagine when it do bromination reaction, there are positions that can actually do. Now, once you get your radical, for example, here you can have your radical here. It actually forms delocalization. You can imagine that it can undergo if, for example, this is the radical that you initially obtained, right? This position here, you can actually stabilize that one with forming diria, right? Diri. Or you have the a radical here, allylic radical, but this one is equivalent. Okay, you have a radical here, it's being formed. Okay, you can do electron delocalization. You can form resonance structures in such a way that pag ma-convert mo diri ang double bond, no, by electron delocalizations or resonance structures, you can form here, form your halogens here. Or here, if you have your allylic position here, and you have your radical here, you can actually form the ripon. So there are too many possibilities to this kind of substitution reaction whenever you have for the formation of an allylic radical because of, again, the formation of contributing resonance structures. Like in this case, you can substitute or you can form the carbon halogen bond by either of this end. But again, for this case, since it's only symmetrical, it's only the same, so you only get 1 allylic alkyl halide. Okay, but in the case of lahi ang imuhang koan, like this case, one of this, 2 of this, then you get different products. And so this one will be one of your practice problem. So have time check 6:04. Ano naman eh, chapter 9. So before we end, I will finish chapter 9. 10.9 rather. So an atom or group bonded to an sp3 hybridized carbon adjacent to a benzene ring is also called a benzylic group. So aside from an allylic radical, so you have your carbon here having a double bond, and this position here, and here is a ring, no? We call this position to be in a benzylic position. And here you have a ring, a carbon having a double bond here, carbon double bond. No, it's similar to like allylic, but because there is a ring, you call this one as a benzylic position. And so the group of atoms that bonded to this carbon here, you call us are at benzylic positions. And of course, the hydrogen connected to your carbon here are called your benzylic hydrogens. So if we compare our allylic hydrogens and benzylic hydrogens actually are much more reactive than allylic hydrogens when we do radical substitution reactions. Why is that again? No, the reason is due to the additional delocalization that is possible by racemic intermediate. So if you remember, you know, when you have an allylic position, there is only 3 atoms in which your electron can delocalize. In the presence of a benzylic ring, no, there are too many atoms that the unpaired electron can go through when it do resonance, when it do pi electron delocalization. So we'll look at later, no, to be the reaction for that. Here you have your methyl benzene. Let's have an example of the reaction at the benzylic position when we substitute our hydrogen here at the benzylic position. So you have your carbon hydrogen here, CH, and this hydrogen is located at the benzylic position because this carbon is connected to a benzene ring. In the presence of NBS or N-bromosuccinamide and light, no, the benzylic hydrogen, hydrogen here is substituted with bromine and the severe product. Okay, and here it said that the benzylic hydrogen is much more active than allylic hydrogen. So here you have a chlorination reaction of hydrogen, benzylic hydrogen. In the presence of heat or light for our halogen, you actually substitute this one to produce your benzyl chloride, and another mole of that, we actually get 2 moles of your chlorine. So one of the hydrogens again is being substituted, and another mole can substitute all the benzylic hydrogen. So this takes place in the gas phase at around 400 degrees Celsius to 600 degrees Celsius, or in the presence of light. Again, this reaction occurs in the presence of light. So you look at here the reaction, no, Cl2 doesn't add to the ring. Take note of that. Instead, it reacts by substitution reactions via radical reaction mechanism at the benzylic position. So you take note of the benzylic position and the allylic position. In the presence of heat and light of our halogens, they will undergo substitution reactions via radical reactions, radical mechanisms. Okay. So how does it happen? Again, you will have here like this. Problem 10.2, it's your problem. You can practice on that. Let's have a check on the why the benzylic radical would can produce your benzylic radical more, or benzylic alkyl halide than alkyl halide. The greater stability of benzylic radical accounts for the fact when ethylbenzene is halogenated. So let's look at here. And the major product actually is when you have your kani. This is the major product instead of kaning alkane dria. No, so you have your CH, you have your hydrogen here, which is 1 degree, and you have a 2 degree hydrogen here. But take note that this is not just a 2 degree, this is at the benzylic position. Okay, we produce actually a benzylic radical. You have here the presence of halogen and light, of course, you actually get this major product here, can substitute in this major product. So the other one is for the 1 degree hydrogen here. We can produce a 1 degree radical. This one is less stable than the benzylic radical. And here we can obtain our alkyl radical here, alkyl connected to an sp3, but this one is of a minor product as compared to your benzylic halide. Okay, so I think that's all. And we will look at why would that be more stable now to produce your benzylic radical. When we go to aromatic reactions, now we'll see how the electron delocalization, of course, at an aromatic position can actually have resonance structures, contributing resonance structures. Once you have this, you can have your double bond here, you can have your radical here, you can have your double bond here, you can have your radical here, and you can have your radical here. Now, you want to see, let's see if you can 610. Okay, so before we end, now I'm gonna show you what makes the benzylic radical actually much more stable. No? So once you produce your benzylic radical, the same way that we have your allylic radical, right? That's very stable now by pi electron delocalization. Here you will have, can actually write a resonance structure that will contribute to the delocalization or the stabilization of our radical. So here you have your radical now, and you can actually write the resonance structure of this. But of course, we'll dig deep in once we reach into the aromatic compounds and we consider a lot of aromatic rings. So today we get our resonance structures. Okay, you will have that. So this one, you can form a bond that, and the other one, okay, one electron. So in the end, you will have your double bond, and you have your radical here, right? And the next is another resonance structure. You can have your, napanisha. Okay. So this is one of the contributing structure, and next is another resonance stabilization. You can have that and that. Okay, and we'll have that. You can actually get your okay, and then you will have your kana, and then you have your radical here. Okay, and then another resonance structure. You'll have your abst. Not finish a double bond here. So you'll try to move, form a bond here, one arrow and another one arrow. Okay, so what you get is actually a double bond, and a double bond, and a dot. Okay, and then of course the other one is once you have your kanina. You will have your one electron and another electron. Okay, And you will have your dot here. Okay. Okay, so you see that there is an electron delocalization. You can see the dot, the electron dot is rotated. No, siya diri. Here you can see the dot, the electron dot. It's located in this benzylic position. You can have this on this position. Okay, and then you can have this in this position, that you can have in this position. Okay, and this one is what you call as resonance structure, contributing resonance structure formed from your benzylic radical in such a way that for all this contributing resonance structure, like you have 1, 2, 3, and 4, we actually have a resonance hybrid for that, no? That you have tick, 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 and then this part, that position. Okay, this is your resonance hybrid. And so you can see that there is greater stabilization with our alkyl radical, alkyl benzylic radical. Okay, so that ends our session for today. I hope that you learned something. And for next meeting, so wala natin na human ang atong chapter 10. So, and of course, I'm gonna be I will upload on problems that you can practice. And the next meeting we'll be talking, which will be after your midterm break, we'll be talking about retrosynthetic synthesis, no? Using one of the reactions that we again learned in chapter 10. And after that, we're gonna do 10.10, and the last one, I think it's polymerization reactions, which will occur also via the radical reaction. So that ends our session, and I can upload later if wala may lingaw. Of course, you're not forced to do activity during your midterm break, but just in case you will be bored, of course, I'm gonna upload an activity, which the deadline will come after the break resumes. So that ends our session. Do you have questions? Wala na. So wala na may question, ora to, and see you next meeting. Okay, so bye everyone. Natog naman siguro mo.
Bye, ma'am. Thank you.